In this chapter, we will dive into the technical details of how transactions work in the Bitcoin network. We will cover the basics of transaction inputs and outputs, as well as the script language used to encode the rules for spending these inputs. We will also explore advanced transactions such as multi-sig, coin join, and stealth addresses. Additionally, we will discuss transaction fees and how they are determined. Understanding these concepts is essential for anyone interested in building or using Bitcoin applications. Multi-signature, also known as multi-sig, is a type of digital signature that allows multiple parties to sign a transaction. In the context of Bitcoin, a multi-sig transaction requires multiple private keys to be used in order to authorize a transaction. This added level of security helps to protect against the risk of a single point of failure. Multi-sig transactions can be set up in a number of ways, but a common setup is the use of M of n multi-sig, where M is the number of required signatures and n is the total number of possible signatures. For example, a 2 of 3 multi-sig transaction would require any 2 out of 3 possible signatures to authorize the transaction. Another common use case for multi-sig is in the creation of a shared wallet, where multiple parties hold a private key and can authorize transactions. This can be useful for businesses or organizations that want to ensure that multiple people must sign off on transactions before they are executed. The use of multi-sig can also be combined with other advanced transaction types, such as time-locked transactions and payment channels, to add even more flexibility and security to transactions. This is useful in scenarios where more than one person needs to authorize a transaction, such as in a corporate setting where multiple people need to sign off on a transfer of funds. In a multi-sig transaction, a certain number of signatures are required before the transaction can be considered valid and broadcast to the network. One potential issue with multi-sig transactions is a bug in the check multi-sig execution. Check multi-sig is a script operation that is used to check that the required number of signatures have been provided. A bug in this operation could potentially allow an attacker to bypass the multi-sig protection and steal funds. This bug was discovered and fixed in a later version of the Bitcoin software, but it highlights the importance of thoroughly testing and auditing code to ensure that these types of bugs do not occur. Pay-to-script hash, P2SH, is a type of Bitcoin transaction that allows for more complex scripts to be used in the output. It is a way to create a Bitcoin address that is not tied to a specific script, but rather to a hash of a script. This allows for more flexibility in the types of transactions that can be created, as the script that is used to redeem the funds can be different from the script that was originally used to create the address. To create a P2SH address, the script is hashed and the hash is then used as the address. To redeem the funds, the script that matches the hash must be provided, along with the necessary inputs, such as signatures. This can be used for things like multi-sig transactions, where multiple signatures are required to spend the funds, or for more complex scripts that can be used to create smart contracts on the Bitcoin blockchain. P2SH transactions are more secure as they hide the details of the script used in the transaction, making it difficult for a third party to know how to spend the funds. Also, it allows for more complex transactions, which is useful for some use cases like creating a smart contract on the Bitcoin blockchain. P2SH addresses are addresses that begin with the number 3 and are used to send transactions to a script hash rather than a public key hash. These addresses are more flexible than traditional addresses, as they allow for the use of complex scripts, such as multi-signature scripts, in which multiple parties must sign a transaction before it can be executed. To create a P2SH address, the script is hashed and then the resulting hash is encoded using a base 58 check encoding, with the prefix 3 indicating that it is a P2SH address. The script can be any valid script, but the most common use for P2SH addresses is in multi-signature transactions. When spending from a P2SH address, the redeemer must provide the full script and any signatures necessary to satisfy the script. In the case of a multi-signature script, this would mean providing multiple signatures from the different parties involved in the transaction. P2SH addresses offer more security and flexibility than traditional addresses, making them a popular choice for advanced transactions and scripting. One of the main benefits of P2SH is that it allows for a greater level of security and control over the funds being sent. With multi-signature transactions, multiple parties must provide their signature in order to redeem the funds, making it more difficult for any one party to steal the funds. This can be useful in situations where multiple parties are involved in a transaction, such as a business or organization. P2SH also allows for greater privacy, as the script used to redeem the funds is not revealed until the time of redemption. This can help to protect the identity of the parties involved in a transaction. Additionally, P2SH allows for the creation of more complex scripts, such as those that can be used for atomic swaps or cross-chain trades, which can enable new types of financial transactions. These addresses are used to encode the hash of a script, rather than the public key of a traditional address. One of the benefits of P2SH is increased privacy. Since the script hash is encoded in the address, It is not possible to tell from the address itself what type of script is being used. This allows for greater flexibility and security in transactions. When a P2SH transaction is created, the script that is being used is hashed and the hash is then encoded into the P2SH address. This encoded hash is then used as the destination of the transaction. When the transaction is later spent, the script that was used to create the P2SH address, known as the redeem script, is revealed and executed. The redeem script must be valid and execute successfully in order for the transaction to be considered valid. This is known as redeem script validation. Overall, P2SH allows for more complex and secure transactions in Bitcoin by allowing the use of advanced scripts and keeping the details of the script private until the transaction is spent. Data recording output, also known as return, is a script opcode in the Bitcoin scripting language that allows for the recording of data on the blockchain. This data can be used for various purposes such as timestamping, proof of existence, and more. Return is a script opcode that can be used within a script to mark the transaction as invalid if the script returns a false value. This can be useful for creating smart contracts or other types of transactions that require certain conditions to be met before they are considered valid. Return can also be used to store small amounts of data on the blockchain, such as a hash of a document or a timestamp. This can be useful for creating proof of existence or other types of records that can be stored permanently on the blockchain. Using return has its limits, as the maximum amount of data that can be stored is around 40 bytes. Additionally, it is not recommended to use return for sensitive data as it is visible to all nodes in the network. Time locks are a feature in Bitcoin scripting that allows for a transaction output to be unspendable until a certain point in time, or until a certain block height has been reached. This can be used for a variety of purposes, such as creating a time-limited escrow, or creating a transaction that can only be spent after a certain number of confirmations have been reached. One of the most common types of time locks used in Bitcoin is the lock time feature, which allows a transaction to be unspendable until a certain point in time has been reached. This is specified as a Unix timestamp, and can be used to create transactions that can only be spent after a certain date and time. Another type of time lock is the sequence feature, which allows a transaction to be unspendable until a certain block height has been reached. This is useful for creating transactions that can only be spent after a certain number of confirmations have been reached, as each block mined on the Bitcoin network increases the block height. Time locks can also be used in combination with other script features, such as multi-signature, to create more complex transaction structures. For example, a time-locked multi-signature transaction can only be spent if a certain number of signatures are provided, and only after a certain time period or block height has been reached. Transaction lock time is a feature in Bitcoin that allows transactions to be delayed until a certain point in time. The lock time is specified in block height or as a Unix timestamp, and transactions with a lock time of 0 or less are considered final and can be included in blocks immediately. Transactions with a lock time greater than 0 cannot be included in blocks until the specified block height or timestamp is reached. This feature is often used in combination with multi-signature transactions to ensure that funds can only be spent by a group of people after a certain period of time or under certain conditions. Transaction lock time is useful for creating time-based conditions for a transaction to be valid. For example, it can be used to create a transaction that can only be spent after a certain date or block height. However, there are some limitations to transaction lock time. One limitation is that it only applies to the transaction itself and not to any of the inputs that it spends. Additionally, transactions that have a lock time of 0 or greater than the current block height will be considered invalid by the network. Another limitation is that not all nodes in the network check for transaction lock time, so a transaction with a lock time may be considered valid by some nodes but invalid by others. This means that it is not recommended to use transaction lock time for critical or time-sensitive transactions. In the realm of advanced transactions and scripting, a concept known as check lock time verify, CLTV, is used to enforce certain restrictions on when a transaction can be added to the blockchain. This is done by adding a lock time value to a transaction, which specifies a specific point in time or block height when the transaction can be added to the blockchain. The transaction will not be added until the lock time has been reached. CLTV is typically used in situations where a transaction needs to be delayed for a certain amount of time, such as in the case of a time-locked escrow transaction. The limitation of CLTV is that it only works for transactions that are not yet confirmed in a block, so it cannot be used to restrict access to funds after they have been spent. A time lock is a feature in Bitcoin transactions that allows for the restriction of when a transaction can be added to the blockchain. This can be done by setting a specific timestamp or block height at which the transaction can be added to the blockchain. One type of time lock is the check lock time verify, CLTV, which is a relative time lock. CLTV is a script opcode that allows a transaction output to be locked until a certain number of blocks have passed. This means that the transaction output can only be spent after a certain number of blocks have been added to the blockchain after the transaction was included in a block. Relative time locks, like CLTV, are useful for creating transactions that can only be spent at a certain point in the future. This can be used for things like escrow transactions, where the funds are locked until a certain date or conditions are met. However, time locks have limitations. The lock time of a transaction is limited to a maximum of about 4.3 billion seconds, about 136 years, into the future. This is because the n-lock time field in a transaction is a 32-bit unsigned integer, which means it can only hold values up to 4,294,967,295. Additionally, time locks can only be used for transactions that are not yet confirmed on the blockchain, which means that once a transaction is added to a block, its time lock can no longer be modified.